Welcome back to the course. In this section, what we will do is we will build a semantic search engine using Elasticsearch. In order to do that, we would use the same Python environment that you have set up in module 1. So I would like to use the same environment, and also let's use the same Docker container that was used in the previous modules as well. So I'm going to go and check if my Docker is currently running. So Docker PS. I don't have any Docker running right now. So what I'm going to do is I'm going to go to our Zoomcamp module 1. I'm just going to share the screen here. You could see it on your screen. From unit 1, we scroll up. You could see from unit 1 introduction section, there was a Docker command that was provided right here. I'm going to copy that command and put it back here and enter. Let's give it a few seconds and you should see the Docker container up and running. And what this will help us to do is to connect to the Elasticsearch locally. You can see on the screen now, the Docker container is up and running. So when we initiate a connection in the notebook shortly, we should be able to get the client connected. All right, so let's go back, open up VS Code in your local and navigate to the same virtual environment or navigate to the same environment where you used, which you used for module 1. So I'm using the same environment here. The only difference is I installed one additional package, which I will talk about. Other than that, everything else should be the same. So what you see here is the overall architecture to build our semantic search. For this module, what we're going to do is we're going to use the same documents.json file, which you should be familiar with, which was used in the other modules as well. We will use the same data set for this class as well. So what you need to do is take the documents.json file, create what we call as documents, which you will see shortly what do we mean by that. So you need to create something called documents. Don't confuse with this documents with the documents.json, though the names are same, but this terminology is used in Elasticsearch. So we need to create from the data set, we need to create what we call as documents. So once the documents are created, then what we will do is we will get a pre-trained model from Hugging Face, and then we will create the embeddings for the documents that we are creating. And once we get the embeddings, then we will push that embeddings into an index in the Elasticsearch. And once the embeddings are indexed into the Elasticsearch, then anytime a user enters a new search query, then what would that do is that will go into the embeddings again. That search query will be converted as embeddings as well. And then that would go and query the Elasticsearch vector database, and the results, the semantic results, will be displayed. So that's the overall architecture. So let's go ahead and get started. A few concepts to understand. There are two important concepts in Elasticsearch vector database. One is called documents, another one is index. So as you can see here, a document is a collection of fields with their associated values. So you will see what do we mean by that. So what do we mean by the associated values? And then what you will have to do is you need to take those documents, right? And you need to add all your documents to an index. So that's what this architecture exactly talks about. You need to take those documents and add it into index. However, there's one step in between where we'll create embeddings, but the idea is you take the document and push it into index. And what is an index? Index is a collection of documents that is stored in a highly optimized format designed to perform efficient searches, right? So think about it. Why the index is going to be the key. Index is exactly like a table of contents in a book. So anytime you read a book, you go through the table of contents, and what that will help you to do is it will help you to go to the right section pretty fast. So you don't have to go through the entire book. You just need to go through the table of contents to go to the right portion of the book. So that's exactly how indexing works here. So we will see that in action. I will show you how that's going to work. So let's start preparing the data set first. So in order for us to get started, what we're going to do is what we're doing is we're opening up document.json file and reading the file. So that after that, what we're going to do is if you look at the documents underscore raw, what you will notice is you can see here the course and the documents. There are two levels of hierarchy right now. However, what Elasticsearch wants is to have everything in like a same level, same hierarchy. So instead of having course on the top and then documents on the bottom, if you want everything to be in the same level. So in order to do that, we have to write a simple for loop again and loop through the docs underscore raw and then basically reassign it. So let's look at the values after this step is done. All right, perfect. So now we can see the course and the questions and all answers in that section, everything is in the same level. So this is good. So this is exactly what we wanted. All right, so let's move on to step 2. So in step 2, what we're going to do is we're going to initiate a package called sentence transformers. We're going to import this package. Recall, I have already installed this package, but I am leaving the package information here. So just make sure to run this command. And once you run this command and then try to import this package. I've seen some issues, not in this environment, but based on my experience, I've noticed some issues happening, especially because of the latest NumPy edition. If that happens, just follow these steps. If you're not able to import after you install the sentence transformer, all you need to do is uninstall NumPy and then follow these steps. You should be able to import your sentence transformer. So what is a sentence transformer? Why is it required? So let's go back to the documentation. So I'm going to bring the sentence transformer documentation here. And then let's go to, and you could see here, the sentence transformer was created by UKP Lab and is currently being maintained by Hugging Face. So what this will help you is, this will help you with a very simple call from the sentence transformer package. You can call the pre-trained models in just one line of code. And you can call the required pre-trained models, and then you can also perform inferencing in another one line of code. So it makes the whole process very simple. So you can see what are the pre-trained models that's available within this particular library. And you have to just scroll down here. You could see that there are a variety of pre-trained models that's available. Again, what is this pre-trained model? These are the models that has already been trained on a certain data set, and it's available for you to start, creating embeddings. So anytime you pass a data into this particular model, what you're going to get out is a dense numeric vector. So with that vector, we're going to pass that vector into our vector database. So that's what we're going to do. So you can see all the performance benchmarks here. You can click on any of these models and you get to see all the required information here. So let's go now. We're going to use all MPNet base v2 in our case. So let's use the same. Let's just copy the code from here. And let's go to the cell here. Then just place it here. And then let's execute it. So this step is now complete. Now let's go and try to perform a very simple inference. And you could see This is a simple sentence. And what you would get back is a dense vector. You see here, what you get back is a vector. That's it. Perfect. So the idea is anytime you pass a certain text to this model, you're going to get back a vector. And you could see the length of the vector. This length is important because different models have different lengths. All right. So now that is done. What we will do is we will set up the, before doing that, let's go ahead and create the embeddings. Remember, the whole idea why we downloaded this model is because we wanted to create embeddings for our data set. All right, so before that, let's go ahead and take a look at the data set once. So in this data set, you could see there are 4 different fields. The first and the third field are the actual data. The section and the course field are like categorical data. So there is not a lot of information or variation that's going to exist in the data set. So it makes sense to either create embeddings on the text field or on the question field. So for our exercise purposes, I chose to do embeddings on the text field. In order for you to do that, what you need to do is you can create a simple for loop, and you just loop through the documents. And for every document, what you need to do is you need to you need to call the model.encode function and then store the vector back into another field. So we'll see that it's a very simple for loop. I'm just gonna put it out here. So go right here. So as I said, you just need to loop through the documents. And after you're looping through, what you're doing is you are calling the model.encode on the doc of text field. And then you're assigning it back into the same list with a different name called text underscore vector. So that's pretty much it. So let's just start doing this. Might take a few minutes. So let's resume after this step is complete. All right. Now the step is complete and the embeddings are created. So let's go back and verify. I think it's in the operations, right? Let's go and verify in operations. Looks like yes. So we have created the embeddings, nothing but a dense vector, and added this back to this document. Perfect. Looks very good. So now what we will do is let's initiate the Elasticsearch connection. Remember, we have already ran the Docker container. So locally, so we should not have any issues. Perfect. So I could see that the connection is established here. Then what we're going to do is as a next step, we need to create what we call as mappings. So now that the Elasticsearch client is created, the next step is we need to create an index. So in order for us to create an index, you need to first create a mapping. So think about this from a database standpoint. Whenever you're creating a schema, so what you need to provide is for the schema, you need to provide the column names, the table name, and then what the data types are, right? So you need to provide that metadata in order for you to create a schema. Very similarly, in this case, you need to provide what we call as mapping, and that mapping will contain all the required metadata information about about the document data. So that's exactly what it's mentioned here. You can read through it, but the first line just calls out the exact statement I just said. It's the process of defining how a document and the fields it contains are stored and indexed. That's it. So you should be very familiar with the mapping already because it's the same, almost the same information that I'm copying and pasting it from module one. And you could see that for the mappings here in the properties section, you could see there are different fields. These fields should be the same fields that we created here. Text section question, right? So these are all the same fields. And you could see the data types associated with it. The only difference is what we have done today is we have created something called a text vector, which is nothing but a dense vector. And we need to also specify the dimensions here. So remember the dimensions, we got it from our inference initially. Let's just go back a step here. Just wanted to show you real quick. So that's the dimensions. It is also mentioned on the model sentence transformer documentation for every models as well. And then you need to also specify the similarity metric in which the text vector should be stored in the vector database. So there are several metrics that's available. So it could be cosine metrics, it could be L2 norm, dot product, Euclidean distance. I'm leaving. I will leave you some reference in the references section, so you can read through it. But by far the most popular type is the cosine or a dot product. All right, so that's pretty much it. So let's just run this. So now let's go ahead and create the index. So you could see here the bottom line here. So this is how you create the index. So you need to specify indices dot create, provide the index name that you have defined here, and also pass all the required metadata that we have created here. And what I'm doing here on the top is I'm creating something called a delete indexes statement. That's because what I've noticed is when you're working through this data set or when you're working on this project, you might realize that you updated the data set or you wanted to change the data type. In scenarios like those, you go and update the mapping. But when you try to create the index with the same name, you will get an error. So in order for you to avoid that, what you can do is as a best practice, every time you can just delete the index if it exists. And if it doesn't exist, you can ignore this delete statement. So that's all this line is doing here. So now let's go and create the index. Fantastic. That step is done. So now the index is created. We already have the embeddings created in the document. So now what you need to do is you need to populate those embeddings or the whole document into the index. So that's what we're going to do here. For that, we need to just loop through the operations data set that we have prepared. And what we need to do is for every document, you need to push the document into the indexes, into the index. That's what the statement is doing. It might take about a minute or two. So let's resume after this statement is complete or this execution is complete. This step is now complete. So let's go back and take a look at the architecture to see where we are. So we have pretty much completed the first portion of our architecture. So we took the documents.json file, we created documents out of it, and then we took a pre-trained model. And in that pre-trained model, we passed the documents to create embeddings. And once that embeddings are created, then we pushed it into the Elasticsearch's index. And so all of the black lines are complete now. So now let's go and build the new search query. So that's the search term that a end user wants to query the data on. And what we will do is we will pass that to the embeddings as well, and then look at the results. All right. So for that, let's go to this section. Let's create the search term here. So the search term the end user wants to search for is Windows or Mac. So the user wants to know for the course, should they bring a Windows laptop or a Mac laptop, or a Windows OS or a Mac OS? And remember, every term that the search term that the user is searching has to be converted it into a vector as well. So that's what this line is doing. And once that step is done, let's go and run this. Now we have to form this query. So you could see here, so we're building a query, and in the query, what we are specifying is, in the database, which field should the database go and search for, and what is the vector that the user is searching. So the user is searching Windows or Mac. So, and that is converted into a vector, and that is what this query underscore vector is taking as input. And then K5, meaning if you want to provide 5 nearest neighbors or 5 nearest documents that matches to this particular search term. And number of candidates, it's nothing but you can think about this like a group of documents that the search is going to look into. And you can play around with this number, like 1,000, 2,000, and then you can play whatever works for you. And that's pretty much it. So now what we are going to do is we are going to pass this to Elasticsearch's search functionality, the search method. So you could see here, there is a search method and it takes the index name, and then it takes the query that we have built here in this previous step. And then in the results, you're specifying what are the fields that you want in the results back. So what I'm going to do is I'm going to just, in the response that we're going to get, I know that the response is mentioned in this particular field. So let's go and run this. Fantastic. So let's open up the results in the text editor. So the first thing what I wanted to show you, mention is, you could see, you remember we mentioned K as 5. So you should see 1, 2, 3, 4, 5. So 5 results. So you got back 5 results. And then you could see for every result, there is a score. So the score, the results are ranked by the highest score on the top and then the lowest score on the bottom. And the score of, anytime a score is close to 1, it indicates that it's a very good match. And anytime a score is close to 0, it denotes it's a very bad match. So we got a score of 0.71, which is a pretty decent score. So let's go and look at the text on what did we see here. So remember what the end user searched for? The end user was searching for Windows or Mac, right? And the first result you got back is, yes, Linux is ideal, but technically it should not matter. So now think about it, right? Nowhere in the query, the end user mentioned whether this is an operating system or a laptop. They just mentioned Windows or Mac. However, this semantic search was smart enough to understand the semantics, meaning the underlying meanings associated with the end user search. So it understood that it's talking about the operating system. So it went and searched for the closest match that matches with the operating system, and it gave you this information. So you can now see the power that you can uncover in scenarios like this, because this is exactly how your Google search works. So recall in the first introduction section in this module, we talked about how the Google is ranking based on whether if Apple is a fruit, your search results will vary. And if Apple is a company, your search results will vary. So that's exactly how semantic search works behind the scenes. So congratulations, you built a semantic search in this section. I also wanted to call out that this is just a very simple semantic search we built. There are much more complex semantic searches you can build. And I also want to show you one little bit of combination of a couple of queries here. So what you can also do is, anytime when the end user is searching, you can use your regular query search On top of it, you can also make sure that the results should be filtered from only one course. Remember, this data set has information from 3 courses. But what if you want to only look at one course? Because let's assume that this user is asking this question in the data engineering Zoomcamp course. So you want the results only from this course. So you can basically chain your search terms accordingly, and then you can filter them. You can query them based on different combinations. That is very powerful for semantic search. Let's run these results. Let's look at the result set. Perfect. So you could see now that the result is only coming from the data engineering Bloom camp. So that's good. Congratulations. You built a semantic search engine using Elasticsearch vector database. I hope you enjoyed the session. Thank you so much for joining. Happy learning.